Okay, so let's get started. So let's see. So again, last week Tuesday, there was someone who was in class who reported so testing positive for COVID right after being in class. I've been trying to be cautious. I've tested twice. So since then, I've been negative. So I'm going to lecture without the mask. I think it's better. Everyone can hear me. I assume this is okay. So great. So then, so I hope the people who did test positive are doing well as well. Okay. So today we're going to be talking about, this will be the last lecture in the dimensionality, so reduction section. What I hope to do is kind of tie everything together. We'll kind of review what we've gone over the last few lectures and kind of pull out the core elements of this. And we'll actually finally solve the problem we posed at the end of the first lecture, where we're finding the best low-dimensional subspace. Again, we almost solved it, but we left out some component of it, and we'll fix that. We'll also see another example of dimensional reduction with a different form called multidimensional scaling. There are kind of 2 points in adding this, or a few reasons for adding this in here. One, it's kind of a different way of viewing the dimensionality reduction problem, and it's a very common technique. And so it kind of fits, it'll fit in with the tools that we learned in this lecture. So that'll be great. The other thing is that the idea of the singular value decomposition, which we've been talking about the last 2 lectures, is something that shows up in lots of data analysis tests, where you're going to do something like the SVD or the eigen decomposition. They're kind of very similar to each other. And that's going to be one of the core computational steps. And that's going to kind of plug into some more kind of complicated algorithm. And this will show you a simple example of that. But there are many, many other cases. A few of them are in the textbook if you keep reading in this chapter, or in some other chapters that they're coming after this. But this will be one that we'll see. We'll kind of actually see another one within clustering, which is going to come next as well. So if you look at the schedule, yeah, so the homework 3 grades have been posted. So homework 3 was the grades were slightly lower than the other homeworks on average, but on average, the class average, I think, is still about where I'd like to see it. So if you had some trouble on homework 3, well, this homework 3 and 4 typically the most challenging homeworks in the course. Try and start early on homework 4 to make sure you're on top of that. There have been a lot of good discussion on Canvas for homework 4 already. It is now due in a week, right? So if you haven't started on that, probably a good time. Definitely after this lecture, you should have everything you should need to complete everything inside homework 4. So start working on that. And then quiz 5 is also going to be on Thursday this week. Quiz 5 will cover the section on dimensionality reduction, the last 3 lectures and this lecture. Okay. So it will be it'll be a lot about things like interpreting the singular value decomposition, how to use it in terms of thinking about high dimensional data, what is a projection, stuff like that. I haven't finished creating the quiz yet, so I don't know exactly what's on it, but that's the sort of stuff. So look at kind of the second questions 2 and 3 on the homework, and that should give you some sense of the sort of things we could ask. So, great. So any questions on the schedule? Great. Okay, so after this, we'll start the section on clustering, which will be more of, you know, some of a change of pace. Clustering, although it'll extend to higher dimensions, you'll be able to think in low dimensional setting will capture most of what's going on. So I think this comes a bit more natural to a lot of people. So if this section has been a little bit hard to wrap your head around, this one, and also often the classification one, which will build on other stuff we've done, hopefully will be a little bit more so natural. Great. And the ways to extend it to higher dimensions are often through the ideas we're thinking about here. So, okay, great. All right, so we started by thinking about, right, the input of our, of this problem was going to be a set A1 up to AN, which is going to be a subset of RD. So we thought of this as endpoints in D-dimensional space, right? And so we're thinking of these points in D-dimensional space, and our goal was to find a subspace, say a two-dimensional subspace, here, and then define some projections of all of these data points. So if I call this subspace here B, I want to find these projections of this data onto here, right? Each of these would be a projection onto B of so a data point, right? And our goal was to find arg min of the subspace, say of rank K, so K-dimensional subspace, in this case, two-dimensional subspace that is minimizing I equals 1 to n of AI minus the projection onto the subspace squared, right? So if I look at those green lines indicate the residual, that's my error. How far I have to project, I want to minimize the sum of those squared errors, right? This is different, it's similar conceptually, kind of, especially in drawing two-dimensional pictures. It looks a lot like the regression problem, but now I'm projecting onto the closest point on the subspace. I'm using a projection. In the regression, I had a supervised problem where I had labeled data, and I could, in the labeled value, I wanted to predict that value, and that's all where the error was measured. I don't have that here. I want to just find the small dimensional subspace. I don't have the supervision to guide me. I'm just trying to fit a shape that captures this data. Okay. All right. And so we talked about, to represent B, we would think about it through a set of these, through an orthogonal basis, V1, V2 up to Vk. This is a subset of RD again. So each Vi, so we're going to have that each Vi is a unit vector. Each Vi is in RD, and Vi dot Vj is 0. So these are going to be so orthogonal to each other, and this is going to be how we represent this basis. Then what we can do is we can project, we can give kind of a new coordinate system in this low dimensional basis. We can think of it as a k-dimensional space. Okay, so then how did we solve this problem? We solve for VB through the SVD, the singular value decomposition. What we did is we wrote A as a product of three matrices, U, S, and V transpose, right? I could think of this as A, U, S, and V transpose. Okay, so where S was going to be diagonal, V was going to be, and U are going to be these orthogonal matrices. And there was a useful way to think about these vectors in V, right? The row vectors in V transpose. So one way to think of this is that the output here, the really important aspects of this were the rows here and corresponding the values here. So I would get as an output sigma 1, which was, this is sigma 1, and a corresponding vector V1, which is the first vector here. Sigma 2, V2. Sigma 3, V3. What this is doing is these vectors are going to be, these are going to be the orthogonal so basis. Every time I add a vector, I'm adding an orthogonal component in a very high dimensional space. I'm slowly building this up, and these guys are explaining so how much how much information is captured. The singular values is saying how much information is captured. That's what's kind of represented in this singular value decomposition. And we told you not to worry so much about the U matrix. If you were doing this on the transpose of A, so it had, say, more, if you're doing it on, say, more, you're trying to do a decomposition over the rows instead of the columns, right? Where the rows were the dimensions and the columns were the data points, then you're doing the same thing with USD. It's just the transpose of it. So it's just kind of like representing the rows instead of the columns. So for now, we can really worry what we're going to read off here. The most useful part for us when thinking about the dimensions as the features and the rows as the data points are the right singular vectors in V. Those give me the orthogonal basis, and the singular values tell me how important are these. Okay, and there's a way to think about the underlying data here as kind of being like this like ellipse. Okay, so there's kind of this ellipse that's fitting this data, and the V1 is capturing, so if V1 is here and V2, V1 captures and V2 captures the axis of this ellipse. How you describe an ellipse, you pick an orthogonal basis, and then you scale along this basis. And the V1 and V2 tell us how to scale that basis to fit the data. And then, they tell you the directions that the data is most scaled in, and then sigma 1, sigma 2, and sigma 3, and so forth tell you how much scale is in that data. And this is the best way to fit this data. That's what's reading off this singular value decomposition. Okay. The other thing that's useful about this singular value decomposition is I can read is to think of my A. Remember, this was A1 up through AN in RD, was to think of A instead as a matrix, right? Where, again, like I needed this to use the singular value decomposition, where this is A1, A2, and AN, where these are the rows in this matrix, right? So this entry here, this entry is A1, is the first row here. And then the singular value decomposition, if I truncate it, right? If I start with A equals U, S, and V transpose here, and I instead decide, well, I'm going to truncate this and make all of these singular values below a certain level 0, and this would maybe be sigma k, right? And then I multiply these back together. What's going to happen is this part and below here are going to be kind of multiplied by zeros. Okay, and the result is going to be these columns here, the k columns here and k rows here, which are left interesting, and then k of the values so along here, and I can recover a sub k as the sum of these components, sigma j uj vj transpose, and this will give me a rank k approximation. This is the best approximation. This is still an element in R n times d, and basically if I measure a k with either the 2 or the Frobenius norm, then this is kind of the optimal way of doing this. That's minimizing this error. Okay, this is another way of thinking about this. So singular value decomposition. Okay, so this is kind of what we talked about so far, and we said, okay, so it looks like I've given you this tool, singular value decomposition. You could use the power method to compute it, but really you're going to use this library built into Python. It's the same library built into any programming language, more or less, to compute this singular value decomposition. Okay, so you're going to compute it, and you can either get this rank k approximation, or you can get this series of k vectors noted by how much they're important, and this can give you a new basis, a new k-dimensional basis that's also have a lower dimensional representation of what's going on. Okay, so it seems like we've almost solved the problem, but we go back, we have not yet solved this problem here. Okay, I wanted to find the best k-dimensional subspace where I project the data on here, and so far, this requires that B contains, so the origin, okay? The basis I found, I'm representing B. What I'm doing so far is I'm finding this subspace. I've got this data. Okay, and then I'm finding these two vectors. So it might be V1 and V2, and I represent these as coming out of the origin. Okay, I'm trying to fit this data right onto this, so onto the subspace, the or K in general, k-dimensional subspace that including this origin point. But it might be the case, right? It might be the case that I don't want to fit the data with the origin. Okay, and this is it's common, in fact, that like a lot of data sets you collect, for instance, they might have all values which are going to be so positive. And if they're positive, then they're not going to kind of look centered around here. They're going to be up in the first first quadrant, the positive quadrant in the high dimensional space. And so kind of forcing your fit to go through the origin is often not a very kind of useful thing too. It's often very, very wasteful of a fit of what's actually going on here. Let me try and draw a different picture, which will maybe make this a bit more clear. And I can actually draw this picture in 2 dimensions now. Okay. All right, so the situation could be that I have data that looks like like this. Okay, and I want to fit this with maybe a 1-dimensional subspace, or think of fitting this with like the best ellipse. Okay, if I do the singular value decomposition, the singular values, the first singular value V1 is going to look something like this, right? And then V2 will have to be orthogonal to it. Okay, so these are going to be the so these are going to be the singular vectors, and I can kind of draw an ellipse that fits this data, but it's going to look something like this, right? This is not really a fit of what the data actually is looking like here. What I would like to do instead, okay, got it, is to instead put vectors that kind of go through the center of the data, V1 or and let's call this V1 prime and V2 prime here, which are going to kind of be centered in the middle of the data. And then I'm going to draw an ellipse that's going to capture it. That's going to look something like this instead. Okay, where I'm kind of capturing the shape of the data. I'm not restricting it to go through this point here at the origin, right? Forcing it to go through this point of the origin is not a useful thing to do here. Okay. Okay. So how do we? This is the actual best kind of low dimensional subspace problem. If I want to find one-dimensional subspace, right, the best one-dimensional subspace should be this one, right? This thin green line I've drawn through here, as opposed to this thin blue line here. That's the thin blue line is not a great one-dimensional representation of the data. In fact, it's capturing the variation from the origin, but what I'd like to do is capture the variation from the mean, right? From the mean of the data. And these things are different. Okay, and so I'd like to capture the one in green here. These are what's called the principal vectors. Okay, and so this is what we want to do instead. Okay, so it turns out it's not that hard to do this. Solving for this is what's called the solution to this is called principal component analysis, okay, or PCA, okay, and it's going to use at its core this singular value decomposition, but I need to wrap it in a very simple sort of step. Okay. Okay. And the key thing here is actually going to be this point here, which I'm going to call C, maybe C of A, if A is the data. So this is the center of the data set. Okay. So just call this, let me just call it, yeah, so C is going to be a vector, A1 bar up to AD bar, where AJ bar is going to be the 1 over n, sum over I equals 1 to n, Aij. Okay, so what is this? It's the average of the jth coordinate. So if I look at all the data points and I look at the jth coordinate, I take the average, and I do that for each of the coordinates. Basically, I'm taking the average of a high dimensional set, right? I can do the element-wise, coordinate-wise average, and I'm going to get this vector here. I can do coordinate-wise average. Okay, and that if you were taking like a median in higher dimensions, there's lots of different ways. What is the right way to do that? There are lots of different answers. That I take the mean in high dimensions. It's just the coordinate-wise mean. This is the right thing to do. And so that's what we're doing here. We're taking the average or the mean in high dimensions. It's just the coordinate-wise average. Okay, that point is going to be where I center my principal component analysis around. And once I've found that center, I just use the SVD. Okay, SVD based on using this as the center of the data. How's this going to work? Once I found the center, I'm basically going to, maybe draw us another color. I'm going to change the location of the origin. So the origin now goes through this point. Once the origin goes through this point, then I can run the singular value decomposition. And I can get the singular values. And the singular values, once I've recentered it, are going to be the principal vectors or the principal components. Okay, so in a picture, this is what's going on. It's possible that the writing out the algorithm is even simpler than the picture. Let me do that next. Okay, so PCA. I'm going to write out a couple of different ways of doing this. One's kind of mimicking the geometric view of it, and then write a linear algebra view, which is more so compact. Okay, so the input is A. This is in A1 up through AN in RD. Okay, so one, I'm going to find so center A1 bar up to A D bar, which is equal to 1 over N, A equals 1 to N of AI. I can just write this in linear algebra notation, in fact. I can just take the average of the vectors and I get this back, okay? 2, for all AI in A, I'm going to create, what do I call this? AI, so tilde, which is AI minus C of A. Okay, this step is called, so centering. Okay, and this is move, I'm going to make CA equals to the origin, right? So after I do this, if I were to recompute the average would then be kind of, is then going to be the origin, is then going to be the all zeros vector, right? So after I've done this, now the center is at the origin. Then 3, I'm going to run, I'm going to call, it's called A tilde, AN. Okay, I'm going to run the US V transpose is going to be the output of the SVD of A, so tilde. Okay, and then the principal, so components or the principal vectors are going to be V1 up to VK, the right singular vectors of A, so tilde. Okay, so these are the principal components. Typically, if I do this, I also want to report CA. You also want to report the center. You might want to keep track of this. It depends. If I just want to project onto a low dimensional subspace, I just need these guys. If I want to actually recover the points in D dimensions, I need the center to do it. Yeah.
Is part of job like changing them back to like uncentering your vectors that you get?
Well, so it depends what you want to do with it, right? So if I want to represent it kind of there are two views of this like SVD based dimensional reduction. If I want to represent them in a low rank subspace that lives in D dimensions, then I need the center. If I want to give a new k-dimensional subspace, then I don't need the center. I just project onto these using the dot products with these orthogonal bases. So I get a new k-dimensional representation, and I don't need the center for that. Right? So if I were to go back to this picture and I were just to take the dot product with V1 here, V1 prime here, I'm going to get one-dimensional coordinates of all the red points that I project them onto that line or that line shifted to the origin. I'm going to get the same one-dimensional coordinates. Right? So that's a great question. Yeah, you had a hand up. Yeah, this is the right singular vectors of A tilde. Let me rewrite that. These are the, let me try a smaller, the right singular vectors of A tilde. Great. Okay, so this is the procedural view here. Right, so it's again, I either just get the subspace, I could actually score these of how important they are using the principal values, which are from the singular values here. I might want to represent them in RD, right? The D-dimensional representation of a vector that has a k-dimensional subspace. I could say that, say, AI hat might be CA plus the sum j equals 1 through k of Vj times Vj dot AI, right? So this would give me something back in RD. If I did this to get it back in RD, I need the center, and then I need also these vectors here. The other thing I could do is I could map them into RK. I could also do AI into, let's call this BI, which is in RK, and I would do this as BI is equal to V1 comma A1 dot up to VK dot A1 or AI. Right, so I get K coordinates, right? So so I can either do one of two things, right? This is either, I have two options. Option one, I map it into k-dimensional space and I just need the vectors. Option two, I keep it in the d-dimensional space, but I know it's on a low-dimensional subspace, right? And for that, I need the center still in the second option. Okay. So it's pretty, yeah. So I'm gonna next, yeah.
With V1 VI, that VK.
Yeah, it's V1 through VK. Yeah.
And then also
AI, yeah. So I'm thinking, yeah, right. So think of this as one data point, AI, and I want to map it to a k-dimensional representation. I'm going to get that k-dimensional representation. I'm going to call BI, right? And so AI is going to be mapped. Each going to given k new coordinates. Each coordinate is just the dot product with one of the vectors I found, right? And so AI is in everything for BI, and I need to do this for all n data points, perhaps. Or maybe this is a new data point I haven't seen before, and I want to map it in that kind of space of maybe taking out the noise of the data, right? I say it's this low ranks or this low dimensional subspace plus noise. Let me just map it in the space that I think removes the noise. That would be, this gives you a k-dimensional representation that maybe if k is 2, you can draw a picture. Or it's in a d-dimensional representation, the same as the original data, but maybe I've removed the noise. So those are kind of your two options. Yeah.
You're getting good points in. You need to like center them first.
No, you don't have to do that. Again, it's a good question. It's a confusing point, but once I could center them first, but the centering is kind of going to yeah, are those going to give the exact same answer? I think they're going to give slightly different answers, but typically you would not center them first. You would just project onto the V1 through V2 or primes in this picture that you've created. Yeah, the centering them might shift them. You know, it's going to enforce that the resulting data is centered around the origin if you center them first. You may or may not actually want that, right? But I could take this vector V1 prime here, and I could draw it here. This is V1 prime, and I project. I've shifted it in parallel, so the red points are, if I project them onto this one that goes through the origin or the one that goes through the center, they're going to have the same sorted order along that dimension, but where the 0 point is going to be different. So that may or may not matter to you. Either answer is okay. Sometimes you want them to be centered around the origin, sometimes you don't. If you center them around the origin, then the singular or the principal values, right, which are the singular values after I've done the centering, that's a lot like the standard deviation. That's why I use sigma there and sigma for standard deviation. And the squared terms are like the variance, because they're the expected deviation from the mean, right? We're removing, subtracting the mean, then looking at the sample expected deviation squared.
I thought you could just basically
Yep. So that's basically what I'm suggesting to do here. My representation of AI hat adds the center back in. I put it before the plus symbol, but you could put it at the end, then you're adding the center back in after I've done this. Yeah. So there are a variety of things you can do, and what the right thing to do is one of these, and they're all roughly doing the same thing, and you can translate between them. Yeah.
And is that sound on number 2?
Yes, J equals from 1 to K. Let me make that a little bit more clear. Good. Great. This seems good. All right. I'm gonna. Okay. So this part is this centering step. When you're dealing with vectors, you kind of don't like to use for loops. Then linear algebra people have said, you never need to use for loops. You can always write it as just some fancy linear algebra trick. And that's the case here. And I'm going to show you that trick because it's common to see and it simplifies. So some notation. So there's something called the centering. So matrix. Okay, this we'll call CN, which is going to be the identity matrix minus 1 over n, this is a scalar, times the all ones vector, outer product with the all ones vector. So this is the n by n matrix, which is all ones. Okay, I'm doing an outer product of a vector of all ones with one of all ones. 1 by 1 is 1. So every entry here is a 1. And I'm multiplying it by a scalar. This is a scalar, right? So this is a 1 over n scalar. So actually, each of those terms now is a 1 over n in every term, if I'm in n-dimensional space here. Okay, and this guy is the identity, n-dimensional identity, where this is all ones here, and these are all zeros. Okay, so ultimately, it's going to have ones. The resulting matrix is going to be n by n, where these terms are 1 minus 1 over n, 1 minus 1 over n on the diagonal, and off diagonal is going to be negative 1 over n. Okay, I'll show you example in Python in just a minute here. Okay, this is the centering matrix, and basically the cool thing is that you can get this A tilde, which is the centered version of A, by just writing Cn times A. Okay, in linear algebra, that for loop of the centering step, I can just do in linear algebra the centering matrix times A. That's why they call it the centering matrix, because it centers the data set. Afterwards, the values are, at the origin. All right, and if you were to kind of unroll what the linear algebra is doing, you'll see that, okay, it's basically doing the same computations, but I've just loaded it into this matrix. Yeah, we'll actually use this matrix twice in the multidimensional scaling. So, but just understand it's basically centering the data. Okay. Okay, so then I can do the centered data. I run the SVD, and then I look at the SVD, and I get the things I need for my principal component analysis, right? So PCA, you can think of as SVD on centered of A, or SVD of Cn times A. Okay, so that's what you should think of as this translation here between these two terms. In the literature in general, if you look online, a lot of times people are sloppy, and when they want to do SPCA, they'll say, "Well, just run the SVD without centering." And sometimes this gives very different results, and the results can be very meaningful, especially if a lot of your values are like all positive. You get very different answers, and it's worth paying attention to this sort of difference here. Yeah. So where is the center being used for what? In the centering matrix, right? So I'm basically, if I were to write out what the centering matrix is doing, this is equal to it's the identity minus 1 over n times A. And if I were to push A through, it's basically A minus, right? Because A times the identity is, I get A back, 1 over n times the all ones times A. Okay, so the 1 over n is kind of taking the average, and the all ones is kind of multiplying all the things in a column. And if you unroll this, you can see it's actually computing the center and then subtracting it in the linear algebraic way. Okay, so we could go through it, but you just need to believe me that multiplying by this matrix actually is doing the centering step for it. Okay, cool. This is principal component analysis. Let me show you something quickly in Python. Let me just show you the centering step, and then we'll take a break and do multidimensional scaling. Okay, so right, so just to convince you these are doing the same thing, I've loaded a very simple data set here. Here, this is 3 data points in 2 dimensions. I can take the mean, right? So the mean of the first column, 1, 2, 3, the mean is 2, if you can see it down here. And then the mean of the second column, 3, 5, 10, the mean is going to be the average of that is 6, right? So the center vector is 2 and 6. Okay. And then I can just subtract the center from everything, right? after I've centered it, -1, 0, and 1, the average is 0. -1, -3, and 4. Again, the average is 0, right? So it's been centered after I've done this. If I do it with the centering matrix, right? So this is NPI, EYE as the identity. How you do that? It's kind of silly. And the NP1's matrix. This is basically writing the centering matrix, and now I multiply by it, and I get a CC again. And so I've basically gotten the same thing: -1, 0, 1. The 0 is 2 times 10 to the -16. So there's some rounding issues going on here, but basically 0 and -1, -3, 4. So it's gotten the same thing up to some very small rounding errors. Yeah.
Someone wrote the NumPy.
Yeah. That I think that's from MATLAB, and that's much older than NumPy. I think they're like, well, you can't just use the letter I, because that's too short, right? And if you write I, I know that's I. And you could have written identity, but that's like 7 letters, and this is 3. That's, I believe, the logic that went into this. So, yeah. Okay, and then just to plot it so you can see, eventually, at some point. All right. And it did plot. It just okay. Great. So beforehand, the red poinsett was not centered. Afterwards, the blue poinsett, you can see the origin is right where my finger is, or I don't know where if you're online, you can't see it, but it's 0, 0, and that's the center of the blue data set, right? So you recover that, right? So you want to center it, and then you can run your SVD. Okay, great. So let's take a small break for 3 or 4 minutes, and then we'll come back and do multidimensional scaling. So let's get back into it. So first of all, before I go into multidimensional scaling, which is kind of a cool thing we'll see, extension, I hope after this kind of half putting it all together lecture, the material's a little bit less confusing. I know that the first time you see this high dimensional stuff with projections, it's a little hard to wrap your head around, but hopefully this has kind of helped kind of see how the pieces kind of fit together here. Okay. But we'll probably have some time after the MDS stuff to ask more questions. We'll move on to kind of a new topic after this. So it's good to understand before your quiz on Thursday. All right. So I want to talk about multi-dimensional scaling. And I don't really understand the origin of this naming convention for this. In fact, multidimensional is a single word, but they abbreviate it like MDS. The premise is going to be a little bit different than what we've talked about for dimensionality reduction. So far, the input is going to be n objects and in a distance function. Okay, D, which is going to be and let's say there are objects in some, let's say, sample space, if you remember, some sort of domain, right? And there's a distance function that's a bivariate function, right? So that it takes in two of these and it reports a real value, right? And you want it so that if things are more similar, the real value is small. If they're less similar, then the real value is large. Okay, and I'm given n objects, and my goal is to put them into a small dimensional space where the Euclidean distance represents them, right? Okay, so the goal is to put let's call these objects x1 up through xn, right? Is to find a1 up to an, which is going to be an rk. So k is going to be so actually for this distance function, let me try and write this as it's not the dimension here, but it's some sort of other distance operator. Again, usually it's lowercase d. Okay, but so we're given where k, usually k is much less than n. Okay, I want to find a low dimensional space. So these are Euclidean vectors, so that the distance between xi, xj is approximately ai minus aj. So now I can use the Euclidean distance on ai on the data set, right? If I wanted to run if I had values associated with these, then I wanted to run linear regression or polynomial regression in a space, I need some Euclidean representation of it. If I want to do clustering or classification with these which we'll see next after this lecture, then I'll want a Euclidean representation of them in order to do that. But I don't have that. I just have n objects and a distance function, right? So an example of this could be like I have n, so cities, and I can look at the price of an airline ticket in between those cities, right? That kind of gives me a notion of distance. It should be cheaper if they're closer together, but maybe flying internationally costs more. There's a fee. So I should somehow cluster the US cities from the ones in, so Canada, flying from Detroit to Toronto, even though they're fairly close, or, so Seattle or Vancouver is going to cost more because of some international fee. So let me kind of separate those a bit more. All I'm given is some distance function, but I don't necessarily have an original two-dimensional representation of those points. I could also think of it, I have students in the class, right? And I've evaluated you all based on your scores on the quizzes and homework so far. And I could think of those as I could have a distance between those. Maybe not the Euclidean distance, maybe kind of another way of measuring the distance, maybe also using your names and your UID numbers. I have some way of coming up with the distance, and I want to kind of draw a two-dimensional picture to kind of see if there are clusters of students in some way, right? How do I draw the two-dimensional picture if I don't have a real good notion of distance? I don't have an embedding of you. I don't have a vectorized representation. Your names are in there. I can somehow measure a distance between your names. They're like edit distance or something, but I don't have kind of a Euclidean representation, so I can't draw a picture. And often I want a small dimensional picture, like two-dimensional thing. So I want to find a low-dimensional embedding where the Euclidean distance acts like the distance I've been given. Okay. Sometimes on the input, you're going to be given a distance, so matrix, and we'll call this D, and this will be an R n by n, and Dij is then going to be this distance xj. So I'm just going to store these distances inside of an n by n matrix often. And typically we'll think of symmetric differences. So xi to xj is the same as xj to xi. Not necessary for this problem, but then this would have some redundant information in, but that's fine. Okay, that doesn't have to be true. Sometimes the airline tickets between two places, it's cheaper to fly one direction than the other. Or if you're driving in a car, you have to make more kind of left turns as opposed to right turns. The left turns typically take longer. Whereas in England, that might be backwards, right? But okay, and so these don't have to be symmetric, but I still want to get a Euclidean representation of these objects. We're also going to use a notion called d squared. This is going to be defined so Dij equals this distance xi xj squared for all of the elements. It's not the same thing if you square a matrix like we did when we're talking about singular value decomposition and eigendecompositions. We looked at the squared diagonal matrix. This is different from that. I'm squaring all the elements. Okay, so it's going to be easier to work with the squared distances, the same way it's often easier to work with kind of the squared air functions. So we're going to actually work on these squared distances here. We're often given just the regular distances as the inputs. Okay, so I'm going to give you describe an algorithm called classical. There are lots of variants on this, depends on how I actually say I want them to be similar. What do I want them to be similar on average? In the worst case, there are different variants of this problem. We're going to look at something called classical multidimensional scaling, which is minimizing something has to do with like the inner products. I'm not even going to write it down, but it's what most people use for this technique, and it works pretty well, and it's pretty easy to do, and it uses the singular value decomposition at the core. Okay. Any questions on the formulation so far? Yeah.
Using the definition mentioned.
What is this? Well, I'll show you how to do this in Python after I write down the algorithm on the slides. Okay. Yeah. Okay. So classical MDS, okay, is what we're gonna. This is the algorithm, and the input here we'll just say is D, which is n by n. So is gonna be my. So is going to be the distance matrix. And we're going to have, the output's going to be in, so the algorithm is, so 3 lines, okay? Each line is going to be doing a lot. The first line is what's called, so double centering. Okay, and I'm going to create another matrix, another n by n matrix, which is going to be equal minus 1/2 Cn d the squared distances Cn. So this Cn is the centering matrix, right, that we used before. I'm centering on both sides. Okay, so I'm centering on both sides and multiplying by, so negative 1/2. Okay, and this is another n by n matrices. This is kind of, and I'll explain this, it's changing from the distances to the similarities. So I'm going to have something where things, if they're closer together, their distance is smaller, m is going to have them so that the values are typically larger. The minus sign is doing a lot there. And the centering is kind of taking the average over lots of choices I can do, and will ensure that the output of this will give my data so it's going to be centered. I'll kind of explain this a little bit here, but this is where this comes from. Okay, so first step is double centering. The second one is the eigen decomposition. Okay, where I'm going to write. I'm going to get the output LV eig of, right? And again, eigen decomposition is a built-in package that you use, right? So this is going to be, M is going to be equal to VL V transpose, and V are going to be these orthogonal matrices, right? So all the columns of V are going to be unit vectors and orthogonal to each other. L is going to be the n by n diagonal matrix, right? With things in the eigenvalues in decreasing order, saying the importance of these things. Okay. And then the third step is I'm going to return a set Q. I guess this would be my output. These are like the Q1 through Qn are going to be the values. And this, I'm just going to write VK LK to the 1/2 here. Okay, so I'm projecting onto the top K components and scaling them by the singular values, right? These are the singular values, right? Remember the eigenvalues are kind of like the squared singular values. I didn't say the singular values of what, but I'll give some intuition on that. And so ultimately, Q is going to be set Q1, Q2 up to Qn. These are going to be in RK. And I'm going to have that the distance between Qi and Qj is going to be approximately Dij in the inputs. This is not an equal sign. This is an approximate sign. An approximate sign. It means they're going to kind of be close. There's the best you can do in some sense, which I'm not going to write down because it's a bit convoluted. Okay. Okay, so this is the algorithm, right? These are the top K, right? VK is going to be is going to be an N by K matrix, right? And LK will just be these, it's kind of the identity. I think I'm scaling each of the things in VK, right? Before multiplying. Okay, so this pretty compact algorithm. And so, I write this down so you can kind of see it, and you could, I think you can implement this. In fact, we're going to do it in Python later, so then you can use the code I have to implement this. But it's pretty short. Let me try and give some, without exactly recovering the full algorithm, let me try and give some intuition of what's going on here. And then I'll tell you how to kind of adapt that a little bit in order to get to this algorithm. Okay. Okay. So why does CMDS so work? Okay. So what we want to think of as the as D Dij, we want to think comes from AI AJ or AI AJ in some high dimensional space, right? So we want to think that there exists some high dimensional vectors. We don't care how high dimension, just very high dimensional vectors where I take the Euclidean distance, and that's what I get for Dij. So I'm going to, if I assume that those exist, then everything is going to make sense. So now I'm not necessarily even going to have those. It could be the distance matrix doesn't, it should satisfy like the triangle inequality and other properties. If this is true, it doesn't need to satisfy those. But the intuition is assume that this does exist. Assume there does exist some input, high dimensional vectors, then what would be the right thing to do? Okay, so we're going to think that there exists high dimensional vectors, and then how would we deal with this? And I wanted to get to the point where the eigen decomposition is kind of like doing principal component analysis for me. So I want to think, okay, so the way to think about that is that I can take this AI AJ, and I can decompose this. And actually, I want to look at the squared version. Again, we're going to look at the squared distance. This is why we want to look at the squared distance, because I can write this as AI squared plus the norm of AI squared plus the norm of AJ squared minus 2 times the inner product AI AJ. Okay. The squared distance you can always kind of write in this squared Euclidean distance, you can always kind of write in this form. This is, if you just looked at scalar values like A and B, and I look at A minus B squared, that's equal to, right? I can write A minus B squared is equal to A squared plus B squared minus 2AB, right? So you probably have seen this sort of decomposition before of a squared difference. I can do this in a vector form with norms too. This also works. Okay. So this is pretty cool that this works, right? And so and in fact, what I want to look at is AI AJ, this inner product, these dot products. Always look for dot products. Dot products are your friends. And I can I can just use algebra to do AI squared plus the norm of AJ squared minus AI minus AJ squared, okay? So I can write the inner product in this way. Okay, now I have the inner product for A and J, but I want to do this, if I want to do this for all pairs A and J and write them in some compact form, well, it turns out that if A equals A1 up through AN, right, then A transpose, and I looked at the ith and the ith and jth kind of element in this matrix, this is AI AJ, this dot product. If I look at A and AJ transpose, if I look at the ith j cell in this matrix, this is an n by n matrix, independent of what the original dimension was. The dimension is on the inside of this multiplication, so it disappears. This is an n by n matrix, and the ij cell is the inner product aij. Okay. So what's great is that if I have this AA transpose, then the eigen decomposition, right? The eigen of A transpose, what I'm going to get out of this are the LV, where these are the left singular vectors of A, and these are the squared singular values of A. Okay, so if I just have all the inner products, this is enough to put them together. I can do the eigen decomposition, which gives me the singular value decomposition. Okay, and then if I project onto, if I take these components along V, the top K components, those gives me coordinates for the n different vectors, right? And scaled by the square root to get the singular values. That basically allows me to recover the best rank K approximation of A. Okay, so A K in RK has AI is basically, I can write this down as VK times LK 1/2, right? This is the best kind of rank K approximation projected into K-dimensional space. I'm just taking, for every one of the rows, I'm taking the first K coordinates of VK and I'm scaling them appropriately. So this is giving me the representation in here from this A transpose. Okay. Okay, but I don't have this AA transpose. I just had the distance or the distance squared matrix. How do I do that? Right? Well, I can if I look at this line here, I can get AIAJ and it involves the squared distance, but what I don't have are these terms, the norms of AI and the norms of AJ. Aha, but I have a choice. The trick, this in green. Okay, the trick is assume that A1 equals 0. Okay, if I assume A1 is the origin in RD is the 0 vector, then AI equals AI minus A1. Right? Because A1 just subtracts 0 off of it. So if I just assumed A1 is going to be at the 0 location, well, then I do have these, right? So then I have AI is equal to DI1. I could have picked anything to be at the origin, right? And if I want to take the average over all choices of A1 being the origin, then I recover this algorithm. The centering kind of does that for me. I want the average to be at the origin, and as you'll see, if I do this and run centering, the end result is that I get a low dimensional point set and it's centered. And I'm centering on both sides because D squared is kind of like A transpose, and one centering's on the left side, one's on the right side. And the centering matrix is symmetric. So one of those is actually the centering transpose. This was actually centering transpose, but it doesn't matter. Okay, so that's kind of the intuition of why this works. Okay, there's some details missing here, but I can turn the squared distances through this transformation into the inner products. Those inner products are enough to give me a transpose, and then I can do the eigendecomposition. And from there, I can project to lower dimensional space. I have a lower dimensional representation just reading off the parts of the eigenvectors. Okay, well, let me just show this in Python. And we'll wrap up here. Okay, so I'm going to import, here's my distance matrix. I need numpy and scipy and stuff here. And you can square it, NP square, squares all the elements instead of D times D, right? So now I have D and the squared matrix. If the distance was 4, now it's 16. 0, 0, 3 is 9, right? Okay. And then the centering matrix, I can, here, there's, this is the centering matrix again, you know, it's symmetric, 0.8 minus 0.2 everywhere else, okay? So then I do this magical double centering step and I get M, and, okay, things that are more similar are kind of larger values, but it's kind of hard to tell, right? It's not, it's kind of a weird thing. Okay. And then I do the eigendecomposition of M, and I get, oh yeah, I forgot, if you don't give it as input, you know, you don't construct M from A transpose, you could have these imaginary values you have to deal with now. These have shown up, right? It's written as this 5.22 plus 0.1 plus 0 dot J. That means it's giving me some imaginary stuff back. So let me trim the real. I'm going to take the square root. So I'm taking it to the power 0.5, and then I'm taking the real part. Okay, so now I have real values after I've done the square root. Okay, because otherwise, if we construct your matrix, you don't have to deal with imaginary stuff, but in MDS, you need to worry about it a little bit. Okay, and then I take the top two components, right? So I took V and I took the first row, the columns 0 and 1. So the first two columns starting at 0, and the first two elements of the diagonal matrix S, right? I printed on S. The first one is 7.2, 2.8. That's how much I'm scaling these by. Okay, and then Q is just V2 times S. Remember, S is after I've already done the square root. All right, so then I just took V2 dot S, that's just scaling the components, and those are my coordinates. The first point is negative 3.3, negative 2.1, and so forth. And I print them, matplotlib, I can print them, and these are now my 5 coordinates in 2-dimensional space. I could have done 3-dimensional, but then I couldn't have printed them, right? And by doing this double centering, I ensure that the origin is in the middle. The average of the points is the origin. If I didn't do double centering, the other construction I showed you, it will work. It will give me basically the same distances, but I won't have the center at the origin, which is kind of a convenient thing to have. So that's what it's recommended to do. It's not much harder to add in that in the double centering step. In fact, it prevents you from having to somehow encode that A1 is 0, which is even messier than this, I would argue. Okay, so again, not too hard to implement, but this is used a lot in visualization. If you have distances between points, you want to visualize them. How do I draw them in 2D? This is the classical way to do it. Okay, great. We'll stop there and we'll do clustering starting on Thursday, and we'll have the quiz. So don't forget your cheat sheets for the quiz.